Sorry, guys. Can you hear me? Hello?
Yes,
Hello?
we can.
Yeah. Can you hear me now? Sorry, I had incoming call and so this disrupts my internet. So sorry about that. But let us continue. So is everything clear thus far? What I did? So basically, we solved basically everything except we still have that minimal distance not expressed. We can express also that part which is over here. So this length here is now given that distance was what I started writing. This distance over here is total half perimeter of the circle, which is pi times r, but r expression here is here, so it is pi vm divided by b and q, and minus okay, minus the length L naught. And so this is the distance of the first particle along the arc to the point where it goes out of magnetic field at the moment when the second particle enters the magnetic field. Okay, let me try to write distance of second, first particle, first Q, when second Q enters a magnetic field. Distance of first particle, let us put into braces when second particle enters a magnetic field from along the arc. To the exit point. And so a particle moves with speed v, so the time period here will be that delta s, by delta s divided by v equals 1 divided by v pi vm divided by vq. Sorry, it's not COVID, it's just something landed into my throat. Minus L naught, and that is the length of that time period. And now finally, the minimal length between them, because now minimal length is so that the arc length is L. Let me make here another figure. So particles are both on the arc. One is here, another is here. The arc length is L naught. So the central angle here is phi equals L naught divided by R equals to L naught divided by V and multiplied by M, and here goes V and Q. And so that this minimal distance here will be, if I divide this by 2, then we can calculate easily from right triangles. It is 2r multiplied by sinus of phi over 2, which is 2 Vm divided by Bq, and sinus of L naught Bq divided by 2 V and M. And this is our expression for the shortest distance. Okay. Now, for some reason, I don't see the screen. I went to the next. Why? Is it still lagging? It was very much lagging. I was drawing, but drawing lagged very much behind. Okay, let me now comment. So I make 2 points. Let's see, 2 particles on the arc. Then I draw a distance L naught between them. Then central angle phi is L naught divided by R. And then I can express the distance between the 2 balls. The figure will soon appear. Yeah, I need to follow actually. See, I'm drawing on my tablet. I do it fast, but it updates on the screen very slow. So, so here is expression for phi, and now express the length over there. We divide it into two, so that we have two right triangles, each of angle phi over 2, so that this will be 2r and sinus of half of the angle. And then we plug in and obtain answer. Is this okay? Is it clear to everyone?
Yes. I have a question, Mr.
Yes, please.
Why the minimum distance will be when the two charges in the circular path?
Why is the distance minimal? Well,
Yes.
if when we have a moment when, okay, here is magnetic field, here is the half arc which it draws, one particle is here and the other is here. Then the distance is, it's quite obvious. I'm not requiring you to show it mathematically, but it is quite obvious that the distance is still decreasing because this goes away in that direction and this goes in that direction. This goes down with velocity v, this goes down with velocity v over there. And now the distance, how will change the distance between them? The distance between them will change so that we draw here a line here and calculate how is one of them is increasing the distance and the other is increasing, because this here, if here as angle alpha, and here between the V and the line connecting points A and B, this angle is formed beta. Then the distance dl over dt equals V multiplied by cosine alpha minus V multiplied by cosine beta equals V cosine alpha minus cosine beta. But because alpha is bigger than beta, obviously, then this is negative, so it is decreasing. Is that part clear now? Yeah, just we need to wait until everything appears on the screen. I wonder why it is so slow, but so is that figure clear? Now everything is finished loading. So Khalid, it is clear? So it is more or less, I think we did before, did we do last time, kinematics. So it is exactly the method from kinematics. So consider the distance change. If V1 cosine alpha equal to V2 cosine beta, then the distance will not change. This is what happens with the rigid bodies. But here we can use the same approach to calculate the changing rate of distance. So if we connect A and B with a line, then angles between the velocities here in one endpoint and the other, project velocities to the direction connecting the 2 points, subtract them, we obtain the changing rate of distance. And we can see that it is negative, which means it is still decreasing. And once both particles enter the circle, two angles become equal and derivative becomes equal to 0. Now, Wessam has issues that I don't know, understand why. I'm not quite clear the question of Wessam. Why L not divided by R? Why is not L not divided by R? Okay, phi, not y, but phi. It is phi, not y. Angle phi. Angle phi in radians. What is angle in radians? It is arc length divided by the radius. This is a very definition of angle in radians. So we have here angle, this angle here is phi. This angle, which I marked here, this is phi, okay? And by definition of that angle, it is the arc length divided by arc length is this arc length here divided by radius r. Okay. Saame siit okay now? So this angle here is phi over 2, and this length here is r multiplied by sinus of phi over 2. That's what I did. All right. Now we can close this topic, if everyone understood. And we can go to the next topic, particles in which move in magnetic field in 3D. In 3D, because now F is V cross B. So we can, if we decompose now velocity into component which is parallel to magnetic field plus component which is perpendicular to the magnetic field, then we can see that F equals V parallel perpendicular plus V parallel cross B, and open the braces. We obtain V perpendicular cross B plus V parallel cross B. But V parallel is parallel to B, so cross product is 0. And what remains is this is V cross B. Now V cross B itself is perpendicular. This whole thing is perpendicular to B, so which means that this does not affect, this force has no component in parallel direction. So F parallel is 0 because it is a cross product with B, which means that the force is perpendicular to B, which means that there is no force parallel to B. Because V parallel to B is 0, this means that V parallel is constant. There is no force, velocity remains the same. Meanwhile, in perpendicular direction, we have equation of motion. Second derivative is the derivative of in y direction multiplied by mass equals V perpendicular cross B. So this is exactly just a two-dimensional motion because we consider now only a component of velocity which is perpendicular to B. So the long story short, if particles move in a magnetic field, then parallel components remain constant, and we have just we can just consider two-dimensional motion of particle in perpendicular magnetic field, like we did yesterday. And so if it means that particles move along circle in perpendicular direction and with constant speed in along magnetic field, which means that this now becomes helicoidal motion. Okay. So here is direction of magnetic field. In perpendicular direction, it moves along circle. In longitudinal, with constant speed, it is helicoidal motion. Is that clear to everyone? Now, yeah, sure, Q is missing. Let us fix this at Q. Q is missing from everywhere. Now, what does it mean? It means that actually, if we consider motion in perpendicular direction, then particles moves along a circular. But now, this fact actually can be used for focusing of particles, particle flux. Now, consider a source of electrons at certain point, and now suppose these electrons all go with the same x directional speed vx, and then they have a small scatter in perpendicular direction. So they have all particles have the same parallel component of magnetic field, but they go all in different directions in YZ plane. And magnetic field is along x-axis. Now, what happens? In upside down view, some particles start that way, draw a circle like that. Some start in that way and they draw a circle like that. And then some start that way and go like that. This is upside down view, which means that view in perpendicular plane. Plane perpendicular to magnetic field. These are the trajectories of all the particles which start at the same point over here. Okay. And then we should notice that all these particles gather into the starting point A after full cyclotron period. After full round of drawing circle, they are back where they started. But now let us combine this with their motion in x direction. So because all they have the same Vx, so they all gather at point A after a certain period of time, which means that after certain travel distance along x, they all are at the same point where they started. So now suppose we have electron beam, electrons going here with speed Vx in x direction, and then we have a screen somewhere. And then they move to screen with helicoidal line, but now they hit somewhere the screen. And the question is, where will they hit the screen? And because of the fact what I described before, it appears that if the distance from the starting point to the screen, L, is a correct one, then they all hit the screen at the same point, so that you can achieve focusing. Your beam, also initially electrons go in different direction, they gather at the screen at the same point. Now, your task is to express L such that you will have focusing. Is your task clear?
Can you just explain what focusing means?
Explain once again. You want me to explain?
What do you mean by focusing?
Well, focusing. Okay, because particles go in different direction. If I put screen very close, and then some particles go in that direction, but the other particles go that direction. Here, electrons hit a screen over a wide range. So you will see, because once electron hits the screen, you see a bright spot over there. But because different electrons hit the screen in different places, you see a big blurred spot on the screen. Now, focusing means that all the electrons hit the screen at the same point. No blur ring, but all electrons hit in the same place. You have one bright spot on the screen only. This means focusing. All electrons which start at this beginning A hit this screen at point B. And your task is to find a distance to this screen where you can have focusing. All the electrons hit the screen at the same point, and you need to express this in terms of the following quantities: Vx, charge m, mass m, charge E, and magnetic field B. You need to express L in terms of these quantities. No assumptions, this is no Hall effect. This is no Hall effect. There are many electrons. Lemmas, there are many electrons. So it is electron beam, which means a huge number of electrons going. Number is not important, but there are many. Exactly because there are many, all the electrons are, some electrons are always hitting. So that's why you see a blur spot if the electron is in the wrong place, that many electrons hit simultaneously. All right. And once you have got answered, please let me know. Mohammed, Vy component is not given. There are different Vys. So this is exactly the reason why you need to have focusing, because in Y and Z direction, electrons go in. There are different electrons go with different Vy, different Vz. That's why if you did not have magnetic field focusing, they would hit in at different places the screen. Vy is not given because there are many Vys. Is the task clear to everyone?
It's not clear for me.
What part is not clear? How can I help you?
What's given in the problem? Like, what's the first direction for the velocity?
In the problem, these things here, which I framed, are given. Vx, m, e, and b are given.
So the velocity wasn't in the x-axis at the beginning?
Particles here, when they start at point A, all the particles start with the same x component of v, vx. This is the x directional speed with which all the particles start. So vx is given. Magnetic field strength is given. Magnetic field is parallel to the x-axis. Magnetic field is in that direction.
Okay.
So that particles move along circle in YZ plane. In YZ plane, all the particles draw circles. But because they have different Vx, Vys, Vz, the circles which they draw in perpendicular plane are all different. Directions are different, magnitudes are different, so they draw all different circles. But Vx is the same for all the particles. So you are given Vx magnetic field, and you're asked about the distance where you can have focusing. At which distance you need to put screen so that you have a nice bright, sharp, bright spot. All right.
Yes. Where is the focusing point?
Focus, yes, you need to actually, this is also a good question, where it is, well, I was in YZ plane. Once again, why you have focusing is that, let us consider here one particle which moves. It starts in, and now I consider, you know, if it's difficult to draw things in 3D, it's always convenient to do two-dimensional figures. And so I am considering now again projection of the trajectories to YZ plane. And so particle starts here from A. I made mark it, let me mark it in blue. So it starts from here and it starts moving. Okay, it moves here, draws circle, draws full round, and after full period it is here. It returns here. Now travel time along full circle is just a cyclotron period. Now another particle starts along other trajectory at the same time, and it travels here along this and makes full period. And now because they started at the same time and has the same full period, as they meet after full period again at starting point A. They were together initially, but then they departed because they had different velocities. So this went that way, this went that way, and then they are no longer together. They started departing, but after a certain time, they after the full period, they are both back at starting point A. So this is the reason why you do have focusing. This will cause the focusing. Zara, is it more helpful?
Yes, but I just wanted to know what's the focusing point in the problem so I can know how many full periods the electrons completed.
So the focusing is that, well, now if you consider only the motion on YZ plane, so the focusing means that the particles which start at the same time gather back after full period. Now in the case of 3D motion, it means that after you can relate the travel time to the distance traveled along x direction. So because they all move with the same speed v along x, so during the full period they travel the same direction along the x-axis. And if you put a screen at that point such that the travel time equals to the cyclotron period, if your screen is at such a point that the travel time equals to the cyclotron period, then the particle has reached the screen, and at the same time it has made full rotation in the perpendicular direction. So in perpendicular direction it has reached the same starting position. So in perpendicular direction, in the direction to perpendicular plane, it's back at A. Okay. In perpendicular, it's back at A, so it means that it hits the screen at the point A. And now this is regardless of its initial speed, so initial velocity in YZ direction, so all particles hit the screen at point A. So please, I already got the answers from Lama and Mohammed. Mohammed has completely correct expression. Llama, you can also put in here an integer. So this assumes you have only one full period, but you can have more than one. So please put in a number n here. Yes, like that. Now, let us wait for the rest of you also to get something. Sorry, I'm trying to. Hussein, your answer is not correct. You have just please check. You have things denominator and denominator mixed. Please check. Hussein, your answer is not correct. Now, I am going to give you one iPad show problem, and please try to solve it. So this will entertain you for quite a long time because it has different parts, and we can go through together to this thing. This is a very nice problem, and you are already prepared for the first part of it. I gave you a link. Please open the link and try solving it. All right. Oh yeah, I sent privately because to Llama because Llama's was a private message, which it got as a reply. I'm sending to everyone here. The first problem when you open this is just you start. It is like iPad show problems you know are long, so you just start reading it from the beginning. It has different parts, so you start doing part 1, and then you can go to part 2. Now Llama, let me see. LSV. Yeah, Llama, that's correct. That answer is correct, Llama. You can also go to the iPad show problem which I sent. Zara, not Llama, but Zara. Zara's answer is also correct.
Sir. Hello, Mr.
Yes.
Yeah, I sent you solution. Which question is this in?
Once again, your question?
I sent you the solution in chat. But I want to know which question is it in the link.
I gave you a link, and link has only one iPad show problem. You start from the beginning. It starts with a cathode ray tube CRT consisting of an electron gun. Can you read this text?
Okay.
These many part problems. You know, iPad show problems have many parts. This is a real iPad show problem. No, ja let us see Hussein answer. No, Hussein, your answer is not correct for the previous problem because period is 2 pi divided by omega, but you have here with omega, you have messed up. This is not good. Please be careful. Omega is BQ divided by M, but period is 2 pi divided by omega. Hussein, all right? Zara, yeah, you were given smallest magnetic field you were given, yeah, but let me see, I'm looking at the solution. Yeah, sure. Cosine, you do have B. So in the text is written, you should express E over M using the smallest magnetic field for which a focused spot is obtained. So you do have B. Accelerating potential. So instead of V, you have potential phi. So you need to express V in terms of the potential. V is potential. No, V is speed. But you need to, let us say U is potential, and then you need to express speed V in terms of U. Okay? Yeah, Zara, I think it's okay. Only one thing, because beta is small, you can just put cosine beta square as unity. You see what? Actually, because you have here particles go over a range of 5 degrees. So actually, you have all different betas from 0 to 5. And they have all the slightly different cosine betas, but because for small angles, cosine beta is approximately 1. So it doesn't matter if there are slight differences, they're almost the same. So you can put in your expression cosine beta approximately 1. Is that all right? Now, let me see what Zara has. Not Zara, but Llama. Let me check. E divided by M. 8. And I think Zara, you forgot somehow. From somewhere you forgot B. Magnetic field should also go into it, right? 2 pi m divided by QB, and then at a certain moment you lost it. But Llama, I think it's okay. Your expression is okay. And as for n, now a question is which value of n integer we should take. The thing is that the shortest distance, as I speak about, is weakest magnetic field by which. So weakest magnetic field means that the longest period, which means that we have only one round, n equals 1. So if you increase magnetic field, it will make more turns, but the smallest field, which we speak about in the text, this means that you need to pick in this expression n equals 1. Is that clear? No. Okay. All right. Let us have a look in the text. In the text, what is written is, let me open the text. They write that you need to express the answer in terms of the smallest magnetic field for which a focus spot is obtained. Suppose now you have your setup, but you start with magnetic field equal to 0. If it's magnetic field 0, all the particles go along straight line and you have a blue big spot. And then you start increasing magnetic field and they are starting to turn. But at first they reach a screen much earlier than make full rotation magnetic field because magnetic field is weak. And then at a certain moment your magnetic field becomes big enough so that they will make a full turn each and you have a nice bright spot. And then you increase magnetic field still more, and they have they make a rotation in YZ plane even faster, and they manage to make 2 turns and 3 turns and so on. But the smallest magnetic field by which you have focusing corresponds to 1 turn. Is it clear now? Zara, did I make it more clear? Okay. I guess you can also try having look on your expression and see that yeah, but if you have your condition for focusing, let us say that d equals v and 2 pi m divided by qb, then you see that if you fix d and change b, and then if you have n1, then you have condition n divided by b is something, and if you take n small, b is the smallest when n is 1. If you take N2, B must be 2 times bigger. If you take N3, B must be 3 times bigger. So yeah, the small, because D is expressed as N divided by B in your own expression. You have a look at expression. D equals 3N 2 pi B, 2 pi M divided by QB. It has N divided by B. If you take N1, B is the smallest. If you take N2, B must be 2 times as big, and so on. Here you have to, because the problem text states that you have the smallest B, then you need to figure out that you need to take the smallest N, which is 1. It just comes from the text. And if that is clear, then you can go on with the second part. Second part is already more difficult. I'm not even very sure if we should do that, because this makes it, we need to have certain relativity, but still it's very nice problem. So you might still, we might still try thinking about it. What is your feeling? Would you like to have try to solve a really difficult problem, or would you ask to take more easier problems to continue with not too difficult problems? What is your feeling? Please tell me in chat. Should we go? Meaning that if we take more difficult problem, we will continue here with part 2. If you feel that you, for the time being, you don't want to have too difficult problems, then say no. If you want to have a challenge, then we say yes. Khalid, yes, something like that, yes. Okay, I have few yeses here, so let us try. Let us then try to solve part 2. Please read the problem 2. Now it is in a sense more complicated case. You have 2 blades, 2 brass plates, 2 heavy metal plates. As there is a tiny slit between them, as shown in the figure. Tiny slit between 2 plates, and there is a source of electrons. So there is, as they say, that it is a source of beta particles. Beta particles are electrons. So you have a source of very high energy, very high speed electrons starting in between the plate. And these electrons will move out from between the plate. But the thing is that you have both now magnetic field, which is parallel to the plate, and electric field, which is perpendicular to the plate. You have both B field and E field. Now, let me help you a little bit. Now, all those electrons which hit the plate, they are lost. They will not be able to go out. Those electrons which hit the plate will not go out. They are lost. Only those electrons which go manage to go parallel to this slit can go out. Is that clear? Only those electrons which move parallel to the plate. Once again, maybe I'll show you here in my screen something. So we have one brass plate, another brass plate. Okay, and here we have source of electrons here. And now electrons which hit the plate, they are lost. Okay, they stay here. If it does, it's lost. If it goes like that, it also lost here. Only those electrons which move strictly parallel can go out. Okay, only those can go out. Now our brass plate ends here. But in between the plate, you have electric field. Let me see now again. Probably I am lagging again. Okay, now not lagging too much. You have here also electric field. So particle which is here, it has electric force down, F equals E times Q. But it has also force due to magnetic field, V cross B. Now, once it goes out, then there is no longer electric field. Electric field is only in between the plates. Now here F equals Q V cross B. This part remains the same before and after. But before you had also electric field. So now once they go out, there is no longer electric field force, but there is magnetic field, magnetic field force remains in between the plates. For the particle to move parallel to the plate, those two must give 0 if we introduce here x in x direction. Okay, fx must be 0. Fx must be 0 because if fx is not 0, force will move the particle to the plate. If there is a force in x direction, the force moves the charged particle to the plate. So for them to move straight line, you must have Fx equal to 0. But now they go out from between the plate and now electric field disappears. So force is no longer 0. Fx is no longer 0 here. And this is what you need to understand for this problem. So the key, what I told you right now, is the key to the solving of the second part of the problem. You need to first understand what is going on. And what I told you, this is exactly what is going on. Is it now more or less clear what happens here? Okay, if it is clear, then go on and try to solve. And now, because I guess this will take you a little bit more time, then again, we'll be having a break after 20 minutes, but I am fairly sure that, okay, Azara, I am ready to answer your questions and explaining once again, but I'll finish first that yes, once we wait, so 20 minutes until break and then 15 minutes of break. But I guess you will be busy with 20 minutes. So basically, I expect you for working on this problem until the lunch, until the first break. And then hopefully we have already something to discuss after the break ends. Is that all right? Now, Mohammed's answer, something like that. Factor, you're missing, Mohammed, you're missing pi and some numerical factors. They are not quite right. Yeah. Please, Mohammed, please make sure that you have period and not 1 divided by omega is not period. 2 pi divided by omega is period. Mohammed, I think you have mistakes in that regard. And also, I think d goes to the denominator. Should go. Mohammed, yeah, please still work on your result. Now, Zara, you wanted, you said something is not clear. So can you tell me which part I should repeat or to make it better for you? Okay, if you read the problem text, it is written. Let us take the problem text. So part 2 begins, and then they say that you have voltage applied. You have voltage applied between the plates. If you have voltage applied, then electric field. Okay, this voltage between the plates. I am drawing it out in the figure. Yeah. Okay. This voltage is electric field multiplied by the thickness. T T here stands for the thickness. So voltage between the plates is electric field multiplied by the distance. All right. So electric field strength is voltage divided by T. This electric field is just because of the condition of the problem. But when plate ends, then the electric field lines go like that. So the electric field becomes very fast, very weak, because here between the plates, the distance is small. But if you go out, the distance of the field lines becomes longer and longer. And so electric field becomes very fast, very weak. So you can say that electric field is only between the plates. So yeah, in between the plates, you have both E and B. Outside of the slit, you have only B. So here I make now in yellow, I mark the region where you have, yellow is not very good color actually, but this is like in the yellow, we have both electric field and magnetic field. Outside of the yellow region, you have only B, only magnetic field. So you need to combine both. But if you have both E and B, then you just take superposition of the forces. So it is, yeah. Now T is not here time. T here denotes distance. Look at the figure. T denotes the distance between the plates. T is the distance between the plates. Meaning, I guess, T as thickness. Zara, no, this figure, so part 2 is completely different from part 1. So don't try to relate to the previous. So previous case was focusing using motion, spiral motion in magnetic field, but now this is completely different. Completely new situation. Okay, very good. Then everyone can work on it. Please go ahead. And yeah, I presume I meet something like 5 o'clock when you have finished your break and also worked on this second part of the problem. If you have something earlier ready, you can just send me either email or chat. I might also be taking my 15 minutes break. Then don't expect me to answer immediately, but as soon as I'm here, I'm answering you. I'll be here around still something like some time. So if you have questions or something, go ahead and ask. So, hello, how are you guys? So, Khalid is asking, okay, phi is angle and S, just let us have a look on the figure. Let us have a look on the figure. So look at the figure, C. As you can see, S is the distance from the brass plate to the screen. So you have.
We don't see, Mr.
Sorry.
We don't see.
Do you have PDF? You have. I gave you a link. You should.
Oh, okay. I thought you are screen sharing. Okay.
Yeah, you should have a look on the figure of the PDF, and you can see that S is a distance between the plate and the screen. Both are cylindrical. Brass plate is cylindrical, screen is cylindrical, and S is distance between them. And phi is angle, which describes the position. So phi is if you draw, to describe position on the screen, because screen is circular, you can use polar angle. Polar angle to describe the position on the screen. Okay.
Okay.
Phi is polar angle, which describes the position on the screen. So how is everyone? Did you manage to make some progress with this problem? So is the geometry clear to everyone now? We have brass plates which are gray in the figure C. In figure C, brass plate is gray, and then the screen is the edge of the circle, the big circle. Okay, yeah, the direction, yeah, that's exactly, Sarah, what you needed to do. You needed to figure out which direction the particle starts going. Apply screw rules and things like that. So it's a little bit boring, but sometimes you earn points for that. How is it the situation? Do you want us to do together part 2 now, or you still want to study it by yourself a few more minutes? Okay, few more minutes. Khalid, everyone agrees? Okay, let us give you a few more. Yeah. Okay, yeah, good, Sarah. Yeah, way to go.
Mister, what's y in figure D?
Sorry?
In figure D, there's something y. What's y?
Um, Figure D, we have coordinate y. Okay, coordinate, what you see on the screen. The black line is the point where the electrons hit. So everything where electron hits the screen, there will be a black dot. Now, you remember I speak before that there is white dot, so it depends which kind of screen do you have. If you have a screen like TV screen or something like that, then it is bright. But if you have like a film, like older days, photography was based on silver photography, which means that everywhere where light hit, it will become black. And then here you have something like that. You have film, which is developed, and then everything where electrons did hit the screen becomes black. And so here the black line is black line marks the points where electrons hit the screen. And now, as you can see, this can be vertically different positions take. So y is the height, the dashed line is the level of the slit. Dashed line in figure D represents the height where you have the slit. So y is how high or how low it is below or above the slit. Is that clear now? Lama says okay. I hope everyone else also understands. Now, Muhammad, yeah, I think now it's correct. Yeah, now your answer is correct. Good. So you can go on with the second part. All right. Okay, got the answer from Zara. I need to figure out, just have a look, because for part 2 it is always like oh, okay, A, B. Let me go through this point by point. So this part is just about this screw rule like things. So to answer a second question, you first need to understand what is changing if we swap polarity. So first, if we have nothing acting on it, then all the electrons move along straight line. If B is 0, V is 0. There is no force, no Coulomb force, no Lorentz force. Electrons move just along straight line. And so this gives the horizontal straight line. Then next, we switch on magnetic field and electric field. And then if electrons go in one direction, then electric field and magnetic field can cancel out. And then they can go out of the plate. On the other hand, if electric field and magnetic field are opposite to each other, then they will not reach the screen. So this means that in one direction they can go out, on the other direction they cannot go out. Now, what happens if we reverse both magnetic field and electric field? Then both forces go to opposite, and if for a certain velocity they were not able to cancel out, they still won't be able to cancel out. So there is a certain direction where electrons cannot go out, because in that direction magnetic field and electric field are in the same direction, and all electrons are diverted to the plate. They hit the plate, they cannot go out. Is that clear? And now, based on screw rule or right-hand rule, whichever you like, you need to figure out in which velocity for electrons they can cancel out, and in which direction they cannot cancel out. And then this gives you an answer for the question, whether it is region A or region B. Is this clear to everyone? Where are the regions? If you look at the PDF, we have region A and region B marked on figure C. Figure C, you see that region A is marked upper half, and region B is lower half of the figure. So magnetic field is from left to right, and then region A and region B. We have up and down. Now, what about the polarity of the plate? We need to, I guess we also need to know which plate is plus or minus, the upper plate or lower plate. So if voltage positive, then what does it mean? Which plate is then so upper plate is a positive when V is positive. So positive charge on upper plate means it is V is bigger than 0. If upper plate is positively charged, then electric field is down, right? Electric field goes from plus charges to minus charges. So electric in this figure, C electric field is from up towards the figure. If I looking at the upper plate, then in that case upper plate has plus charge, which means that the electric field between the plates is down. Is this clear now to everyone? So we have figure here. Here is brass plate. It has plus charge, which means that the electric field is towards the figure. And now here is the line which separates region A and region B. This is upside down figure. Electric field is shown as here, and magnetic field is from left to right. And then we have here, this is region A, and this here is region B.
So we can't see the screen.
Okay? Let me make it so that you can see it. Can you see now?
Yes.
Okay. I think the figure is should be more or less clearer now. Yeah. Now you should because if electron moves in between the plates, it moves here. If it moves in that direction, it has electric field to which direction, and magnetic field to which direction, magnetic force to which direction. So it can go out if they are in opposite direction. It cannot go out if they are in same direction. So you need to figure out in which direction they can compensate. Lorentz and electric force can compensate. In that way, direction you will see this, something on the screen. In the other direction you cannot see. Now on the figure you are shown a part where you can see electrons. All right. Can everyone see the screen? I am sharing, yes. Khalid is asking if I am sharing. Can you see the screen now, everyone? Okay. Zara is not seeing with strange. Some of you are seeing and some are not seeing. Very strange. Let me stop sharing and start again. Maybe then it will work. Zara, can you see now screen? And now it's fine, yeah. Okay, very good. Now, can you answer now the question? Which direction we are seeing on which direction is shown? Which region is shown in the figure D? A or B? Yeah, top is A, down is B. Yeah. Which one? Which one is shown in figure D? Because as they say, film is taken either from region A or region B, and you ask which region, from which region it is taken. The thing is that the film was in a single region, and what happens is that they change polarity of magnetic field and voltage, but the region remains the same. So it cannot be so that one part is from one region, the other is from other region. Film was always in a single region, either A or B, but not in both. So the question is, from which region? So in this part, you just need to think about direction of the forces, nothing else. You need to pick the region where electric field, electric force and magnetic force are opposite. This is where particles can go out. Yes, yes, Sarah, this is correct. Okay, Sarah, you don't understand why there are two trajectories up and down. Well, this is because they change the voltage and magnetic field direction. You see, they make three, expose the film to electrons in three cases. First, there is no B, no E. Second, they apply electric field down and magnetic field from left to right. And then they swap. Then there is electric field up and magnetic field to left. And in all these cases, particles can go out when the two forces cancel out. But once they go out, the direction where they go depends on the magnetic force, because outside the plate, inside the plate, they move straight line. Outside the plate, they are curved because there is no longer forces are in balance. If they are out, only magnetic force exerts force. No electric force, no longer. but magnetic field was swept. First it was from left to right, and then it is from right to left. And so as compared to those two cases, the Lorentz force was reversed. And if one case particles went up, then now they go down. And that's why you have two traces. One case electron went up, and in the other case they went down after you change the direction of the magnetic field. Okay. Khalid, how are you? All right. Once again, let us have a look on the screen. And now we have a plate, which is the inner circle here. And inside the plate, there is electric field down. Outside, electric field is zero. But between the plates, in the region of the plate, which is this part here, this is the plate region. There is in the slit, side view. This is top-down view, side view is like that. Here is plate, here is plate. Here is a slit between the plates. As long as particles is in between, then it has, let us say, electric force is up, and magnetic force is QV cross B is down. And now they cancel out, so that particle moves along straight line, nicely along straight line. Okay, now it goes out, and now electric field disappears. Now it starts going down because we have now magnetic force down over there, QV cross B. And now you have here, inside view, you have screen. And then here is what you see on the screen. Here is a dot on the screen. Okay. So now it went down. Once you change both E and B, then you have a situation, a similar situation, but everything is other way around. Now you have still two plates. Particle goes here. But now we have electric field is down because electric field was swept, and magnetic field is up because magnetic field was swept. But they still cancel out because they are in opposite direction. And so particle moves now horizontally, but once it goes out, it starts curving up now because of magnetic force. And now let me see, is it delagged? Yeah, it's not delagged, you already see it. Okay, so that's what's happening. And now you need to figure out in which direction particle needs to go. Whether it needs to go up or it needs to go down. So that in which direction electric field, electric force and magnetic force are opposite. This you need to figure out. Khalid? All fine? Okay. Now, can anyone else tell me which region it is? I think Zara got it right, but what about the rest of you? If you have region name, type in. Lama Billy is believing it is A. we need to have the two forces opposite. Khalid, we need to have opposite. The particles go in all directions. Particles go in all directions. And Lorentz force, you need to figure out, you just need to figure out the directions using screw rule for Lorentz force. You need to have Lorentz force opposite to electric field. You have all directions. So particles from between the plates, from upside down view, particles now go in all directions. They start from here and they go in all directions. Now it is lagging now a little bit. Just wait a little. Particle goes in all directions, but most of them will hit the plate and cannot go out. Only in a small sector in the correct direction can the two forces cancel out. Only in that direction they will not hit the plate. Only in that case there are some electrons which will not hit the plate. Most of the electrons will hit the plate either way, but very few for which the two forces, electric force and Lorentz force, are exactly equal. Only those can go out. This is only a very small fraction of electrons. All right, let us see. We have consider region A. Consider region A. We have an electron going up. And magnetic field, let us consider when the force, the initial situation, when magnetic field is from left to right. B is that way. And electric field is that way. Now, if our electron moves that way, where is the force direction? Which direction is the force? Who can tell me? Magnetic Lorentz force. Electric force, which direction is electric force, which acts on electron minus E, charge of minus E? Where is the force acting on electron? Who can tell me? Yeah, it's opposite, but actually, guys, pay attention that actually the charge of electron doesn't matter because whether it's positive or negative, we need two Coulomb force and electric force cancelling out. So actually, charge, sign of charge doesn't matter. But let us do it with negative charge. Yeah. So if velocity, here is velocity, now, right? So V cross B, so this is direction of V, this is direction of B. We rotate screw now as shown here in the figure. Where does the screw go? Rotate clockwise, and where does the screw go? It goes down, am I right? So V cross B goes down, but force goes up because force is negative. Now, but electric field is down. Electric force is also up. Is that right? So we can see that if the electron goes up, as here, then magnetic force and electric force are in the same directions. They cannot go out. Now, what happens if we change the electron velocity opposite? Now, electron goes down. What happens with the direction of the forces? Electric force will not depend on velocity. Electric force is still towards us. But what about magnetic force? Magnetic force field changes sign because magnetic force is depends on V, and it is V cross B. So now magnetic force, it was up, but now it is down. So now they can cancel out. So it means that electron goes down, and if it goes down, it is region B. Okay, this is clear to everyone? All right, and then we need to go to the third part of the problem. And now you have here a figure, a graph, where you can use actually a data table. Not that I don't think we are going to use the graph, but the data table which is above, the displacement as a function of angle phi. And how can we use now these data here? So now you need to determine the maximum kinetic energy of the electrons. Beta particles are electrons. So it determines the maximum kinetic energy of the electrons. How can we obtain that? And in which way does kinetic energy come into play here? Who can tell me? Here, in order to be able to solve part 3, then we need to understand what happens and why things start depending on the maximal kinetic energy of the electrons. So actually, regarding kinetic energy of the electrons, what it is, the voltage V has nothing to do with kinetic energy, because we have a source of beta particles. This is something, some atoms which undergo nuclear decay, and so one nucleus splits into several nuclei, and during that process some electrons are radiated. Now these electrons can have different energies, but typically the energy is fairly big energy, much bigger than anything you obtain here from the voltage. So just electrons start with a fairly big kinetic energy from the point where from the middle of the drawing. So there is initial kinetic energy of the electrons which goes there. But electrons, because there are different reactions and different possibilities, so there is a range of energies which electron can have. Some electrons are faster, some are slower, but here we speak about the fastest electrons, which have the highest kinetic energy. Now, how does come into play here the speed of the electrons, the maximal speed which they can have? Maximal energy means maximal speed. Who can tell me why this? Where does it come into play? How can we connect the data? Which again, which data here are related to the maximal kinetic energy? Please think about it. Yeah, sum of forces is 0. That's right. In order for a particle to go out, sum of forces needs to be 0. Zara, we can now let me comment what you write. Zara wrote me QB is mv squared divided by 2. Yes, this is somewhat correct. So this is correct in classical mechanics, and this works here also to a certain degree. Like you can understand things definitely with QB equals mv squared over 2. However, because here, as it turns out, energies are fairly big. You have actually fairly big energies, so you need to take into account also relativistic effects. As a matter of fact, let us keep that for the time being. Let us say that QV is mv squared over 2, but later on we might need to do it more precisely. But then, okay, we have we can relate at least speed of electron to the energy. But now, how can we determine V? We don't have voltage, or do we? We do have voltage, but this QV has nothing to do with kinetic energy of the. Wait, Zara. No, actually, what you wrote is not correct. You know why? This is exactly what I explained. So that your expression, Zara, your expression is correct. When, let me take another figure here. If we have here like one electrode, and here is another electrode, and here we apply here voltage V, and the electrons start here, and then this voltage here accelerates electron. So electron goes through this voltage difference, and then if it starts, let us say V equal to 0, this is voltage, let voltage make V capital. If it starts with 0 speed, then it goes out here with pertons V, so that mv squared divided by 2 is E times V. Then your expression is valid. However, here is a different situation. Here we have two plates, and here we have source of electrons, and source of electrons go to all the direction with certain kinetic energy, initial kinetic energy. Let's write it E sub k. Initial kinetic energy E sub k, which is big. Now we have voltage applied here, V, but this voltage only creates electric field. Particles go perpendicular to that electric field. This electric field does not give any energy here because particles move perpendicular to it. Does not give energy. So electrons move with initial kinetic energy. There is no energy related to the voltage which is there. Even if that voltage V would give some energy, that Q times V, well, E times V is still much smaller than the initial kinetic energy here, because they start with very big initial kinetic energy. All right? So please think about how to relate now things here to the kinetic energy, from where you can have anything to get started. Yeah, a relativistic part. Right now, don't worry about the relativistic part. Just now, for the time being, just think about speed is bigger when energy is bigger. For the time being, Khalid, you don't need, later on, yes, consider relativistic, but right now, forget about it. And yes, since magnetic force depends on the velocity, then we need to have conditions that the sum of the forces is 0. So now, yeah, exactly, tell me which data from the problem text we need to find the maximal speed. Angle min, so which point you mean? Just from the data, tell me from the data, which point? Which number from the graph or from the data table? Okay, yeah, 23. Yes, right. That's right. And can you now write it more specifically? So what is the condition? That is right. Khalid has a good suggestion. So what we care about is the minimal angle. Can every one of you see why? Yeah, exactly. V is ut b sinus theta. So that U is voltage, I presume. U is voltage, so that U divided by T is electrical field. And then you can see that if we have a big theta, then V is small. And if we have a small theta, sinus theta is small, then V is big. And so when you have no longer electrons with great enough speed, then the trace will end. And then there are no more particles which can go out. And exactly because of that, what you need to take is the point where the trace ends. Did every one of you get this point? So with that now, we already have from the answer of Khalid velocity. V is ut b u divided by t b sinus theta. So we do now have V. Now, how can we get now from V to the kinetic energy? Here is the point where we need to apply the theory of relativity. And let me write now here on the screen. Can you see everyone on the screen? Okay, so we have kinetic energy, what it is in the theory of relativity. Kinetic energy is a difference between relativistic energy, which is the relativistic mass, but relativistic mass is rest mass divided by 1 minus square root v 1 minus square root of 1 minus v square over c square. This is relativistic energy, relativistic mass, and multiplied by c square. You know that mc square is a famous formula, right? So m is relativistic mass, so that is m not divided by square root of 1 minus v square c square. And now this is the full energy, but kinetic energy is, we need to subtract the rest energy. So kinetic energy is this guy here. Now here we know V, and then we can calculate the kinetic energy. So it's quite easy task. Now Zara is saying you cannot see what you cannot see. Zara, you cannot see screen now. Oh, I have written in green. Do you see green text? I wrote in green. Zara, let me draw here a orange frame to the formula. Can you see the orange frame? Zara? Okay. This is what I wrote. Kinetic energy is a difference of relativistic full energy and relativistic rest energy. So in this formula, Khalid just wrote for us the speed V, and all we need to do is plug in over there expression for V. And yeah, if v is big, this is what you need to do. If v is small, then this simplifies to a classical expression. If you make if v over c is small, then you can approximately express square root of 1 minus x square, and then you obtain as an approximate expression mv square over 2. All right, but with that, I think we can go to the second part of the problem, last part. So, because now, I think we have already here, actually, basically the third part is done. The third part is done now. We can go to the last part. And yeah, then go ahead and think about the last part. Now you should be already quite, you know, quite enough to be able to proceed with the last part. Now you need to use the data, the other data in the data table, I guess. I can give you a small hint here, actually. Let us go to the previous page. And here, let us look now, let me frame it also with something. Let us like purple. Let us frame this in purple. Let us consider this figure here, okay? Now, electron comes and starts curving. Here, this black line here, electron comes and starts curving here, okay? Now, this part here, which I now make also in blue, this part here is a circle. So you could, well, how you could do it is to calculate by Lorentz force and all what we studied yesterday. However, here actually it might be easier to do it a little bit different way, because this is a very small arc. Actually, if you look at the numbers of the problem text, actually the values of y are small as compared to s. So here is s, and here is y. This is y, okay? What we have is y is much smaller than s. So this means actually this is a very small piece of the arc, and actually you can neglect the change of velocity, direction of velocity in the Lorentz force. You can say that it moves along with a constant Lorentz force, like free fall acceleration with constant acceleration. Here, motion with constant acceleration because of Lorentz force. This gives you a very good approximation, which is much easier to use here. So you use approximation. Acceleration is constant. Acceleration due to Lorentz force. Now, Wessam is asking why do we have minus m sub 0 c square subtracted. Wessam, in relativistic case, the kinetic energy is defined as the difference of full energy, full relativistic energy, which is relativistic mass times c square minus rest mass, which is rest mass times c square. This is just the definition of relativistic kinetic energy. mc square minus m naught c square. A is acceleration. Acceleration. So in order to use, in order to solve this problem, you do not need to consider circles, but instead, because you have a very small piece of circle, so that the direction of velocity does not change much. then you can assume this as a motion with constant acceleration. Lorentz force changes direction, but the change is very small. So you can say, assume that the projection of acceleration to the vertical direction is basically constant. Lorentz force you can assume as particle moves in that free space over there, outside of the slits, Lorentz force remains constant. This makes your calculations easier. Lama, is it clear? Okay, then if it's clear, then please try to solve this. It's the last part of the problem.
I want to go to Caitlin Collins right now because there's new reporting on the increasingly tense.
Sorry about that. So how are things going? Do we have any progress? Guys, do you have any progress? Okay. Yes, that's not very easy task, so it's okay to. But yeah, we would. It would be preferable if we could finish it more or less before the second break. Second break is coming soon, so let us try to finalize. Khalid, no, A is constant does not mean necessarily that motion is not circle. If Khalid, answer me, if you have constant acceleration motion, what is trajectory? What shape of trajectory is if you have constant acceleration? What is your shape of the trajectory if you have constant acceleration? The other guys can also help. Yeah, no, constant acceleration, what shape it is. Other students can also help answering this question. If you have constant acceleration motion, what shape it is? No, not line, constant velocity line, but constant acceleration. Parabola, of course, parabola. Now, draw a parabola. And now draw a circle. And now zoom in here. Zoom in here. Is there any difference between those two? If you zoom in a small range, near the tip of the parabola. These two are, if you take a small range, small angles, okay, here we consider small range of angles. If you consider small range of angles, then actually parabola and the shape of parabola is very close to that of the circle. Okay, you can also you can do it even mathematically. Okay, shape of this circle is x square plus y square is r square. Now let us write in the form that x square divided by r square plus y square divided by r square is 1. So that y is equal r square root of 1 minus x square over r square. But you know the formula square root of 1 minus delta is approximately equal to 1 minus delta over 2. Do you know this formula of approximate calculus? This formula here. Khalid? Yeah, okay, yes, you know. Now let us plug it in. And then this becomes r multiplied by 1 minus x squared divided by 2r squared. And now you can see write as r minus r x squared divided by 2r squared. So 1r cancels out. And then you have parabola. You have y as a function of, and you have x squared over there. So this is parabola. You can see that if you use small angle approximation, which means that x divided by r is much smaller than 1, then you have you can substitute a circle with parabola. This is exactly why you can do we can do that. Yes, the trajectory in long term would be a circle, but we consider only a small segment of the circle, so we can consider it also as a parabola. All right. Now, we'll be having a break soon. I think it was 1940 to 1950 or something like that, was it? Okay, so let us do that. Let us have a break, and after break, let us solve it together. We solve it together now because as long if you have something, some result, you can send me. But we solve it now because we want to move on with some more topics because well, we have only tomorrow's day, and we still want to have a few more things to go through. So after break, we'll discuss the solution here. How long break? 10 minutes break, but so 10 more minutes for solving. So we start solving together at 1950. Okay. So perhaps some of you can solve the last part by 1950, but if not, then either way, we'll do it here. How are you guys? Are you back and ready? Aha, Khalid has something. Let us see. Let us see. Shall we do it together? All right. So now what we need apparently to consider is particle going on the arbitrary direction. And then we go take here which way is it? Theta was now again. Theta was if angle phi was the angle between okay 90 degrees is 90 degrees correspond to a direction perpendicular to B. So let us write now for Lorentz force equals to QB and V and times sinus phi. And then when particle goes outside, there is only Lorentz force. And then this equal to, now we make a projection, we project forces to the vertical direction, and then it becomes m and second derivative of acceleration. A second derivative, time derivative of y coordinate, acceleration in y direction. And from here, because initial velocity, as at the moment when it goes out from the slit, it has a zero coordinate, zero y. Y is 0 and Vy is 0. Okay, let's see, maybe you're more convenient if I put it here, y component of the acceleration. Now, with that, we know that y equals y naught plus v naught t plus gt square over 2. This, you know, acceleration, not g, but a. Let us put it here, a t square over 2. Now, this is 0, this is 0, remains only a. So this becomes now acceleration is q b v sinus phi and divided by 2m and t square. Now t square, t is t's time. Here is t was also previously thickness, but now it is time. Now t is the speed of the particle, which is now v. It is distance s. Oops. Now, how can I get rid of that? I have always, once I get that, I have difficulties getting rid of it. No. Okay, here it is. T equals v s divided by is s divided by v. And so all things together becomes equal y equals q b s square sinus phi and divided by 2m and v, something like that. Yeah. And now here is y as a function of phi. But here, what we have here is relativistic mass actually. So this guy here, m equals m naught divided by square root of 1 minus v square divided by c square. So now we need to get rid of everything, and we want to have m divided by q. Actually, m divided by q is over here. We do have q is here and m is here. This is what we want to have. So basically, we have something here, but actually we still haven't been used one condition. One condition is that the particle is at equilibrium with the electric field. So conditions that particle is at equilibrium with electric field is that V sinus phi multiplied by B equals electric field, which is V divided by T. U divided by T. Okay, this is conditions that particle when it moves in the slit, electric field and magnetic field are perpendicular to each other, so that it will move along straight line. So we need to substitute everywhere V with that expression from here. So actually, from here we have that V equals U divided by B, T, and sinus phi. And now, let us see. Let us take everything. Let us simplify things. Let us multiply. So now, well, actually, the task right now has become mathematical task. So here are the physical things. Physics is here. Y is is expressed in terms of sinus phi, and we also have additional constraint here. We relate V to sinus phi. So this relates Y to sinus phi, and second expression relates V to sinus phi. And now we need to modify it mathematically so that we have we need to eliminate V from here. And then let us take the first equation, this one here, and multiply everything by 2mv and take the square. We take the square because in that case, that square root from m goes away. So or maybe yeah, okay. Let us rewrite it rather in that way. That y square equals 4y square v square 4y square v square equals, and now and also m naught square. Let us put here, but because in the denominator is m, which is m naught divided by square root. In the whole expression, square root goes to the denominator. So now at the right hand side becomes q square b square s to the fourth, and then sinus square phi, and then 1 minus v square over c square. And so now we have here now we can substitute. We need to substitute v, get rid of v. So let us divide everything by v square. Let us divide everything now by v square. And then this becomes now 4y square m naught square equals q square b square s to the fourth, and then sinus square phi divided by v square, and then minus q square b square s to the fourth, and then divided by c square and sinus square phi. Something like that. Now we have v only, v square only in this term here. and we need to plug in v square from this expression here. We now plug in v into here, so that the whole thing becomes now let us divide everything by q, because we want to have m divided by q. We want to have m not divided by q, so let us divide this also by q, and then we obtain 4y square m not square divided by q square equals, yeah, right, we plug in v square as sinus square over there, so that we'll have q square b square s to the fourth divided by voltage squared. Thickness t squared goes to the nominator, and then we have yeah, b square. What happens? B goes to the fourth actually once we plug in here b to the fourth, and then we have sinus to the fourth power of phi, and then the last term is over here minus q square b square s to the fourth divided by c square and sinus square phi. I'm not sure now, I did it just very fast here with you. I'm not sure if I made some mistakes, but that's basically how you're supposed to do it. And then we have now what I have expressed. We have expressed y as a function of angle phi. This is what you are given. And then from this graph here, you would need to find this factor here. So basically, you need to fit, using the data, you need to fit this dependence. Now, how you can do it is that we can plot something like we can plot something like now I'm just a little bit worried, maybe I made some mistake with sinus, because I have sinus to the fourth and sinus square. So we could plot y square as a sinus square phi. Oh right, yeah, I know what. We plot, we divide this now by sinus square. We divide this by sinus square, and then we obtain what? Then we obtain 4y square divided by, let us write a little bit different way. I write here y square divided by sinus square phi multiplied by 4 m naught square divided by q square equals q square b to the fourth s to the fourth t square divided by voltage squared and sinus square phi minus q square b square s to the fourth divided by c square, and that's it. Now what we have here is, let me show. First is this thing here, and then we have sinus square here. So if we plot now, so that y square divided by sinus square phi is in vertical axis, and in the horizontal axis is sinus square phi, and then there is a straight line, okay? And then the slope, with calculating the slope, you can calculate actually the factor of the slope. So this slope here, tangent of alpha, from here you can calculate m naught divided by q. So there is still some math to do, but basically this is a fundamental approach. Now Lama is asking why there is q square on the right hand side of the equation. I might have made a mistake because I wrote it fast. So let me see which equation you have in mind, Lama. Which equation? q square, because I took everything to square, I guess. We had expression for y, this equation marked with star. We had this equation marked with star. We took into this to square. And
Didn't you divide by q squared?
sorry?
Didn't you divide by q squared?
Oh, yeah, sorry. Sure, very good. Thank you very much. Actually, because we divided by squares, this went away. Thank you very much. Yeah, sure, it goes away. This is very point that what goes in here is only mass to charge ratio. Yeah, so that's a good
Question. So after we get this equation, how do you calculate the final answer?
Oh, so what you now need to do is you need to plot y square over sine square against sine square phi. And then you can calculate if everything goes fine, this will be a straight line. It will be a straight line, and then the slope and the point where intersects gives. So this will be now y square over sine square phi is a plus b sinus square phi, where a equals, now let us see, a equals this guy here, actually a is negative, a is minus b square s to the fourth divided by c square, and also we need to carry over that factor from the left hand side, so 4 goes here, m not square goes here, and q square goes here. This is a. Now, what do we know? We know B, we know S, we know C. Actually, by calculating this A, we can already find actually this thing here. The only thing what we don't know is that one here. So from here we can say that m naught square divided by q square is the slope, tangent of the slope. No, this is not tangent, this is intersection point. Intersection point of the slope. 4c square a minus sine and divided by b square s to the fourth. And I guess you can do the same with the slope, because slope has also known quantities, voltage and distance t. Yeah, did I answer your question? So you need to take data, you need to plot and find the parameters of the straight line. And based on those numerical parameters of straight line, meaning the factors a and factor b. Lama, is it okay?
Oh yeah, okay. Now I understand.
Mm-hmm. So, by the way, this is very typical and very quite often at the Olympiad, you need to use this trick. So this is called linearization of a curve. So you have some possibly quite complicated dependence, like here. You have angle and you have displacement y. And there is a non-linear complicated expression. But you need to find such axes for vertical and horizontal direction that this line becomes straight line, and then you can plot and obtain nice straight curve from the plots. This is also the experimental technique. What you need to know that if you make experiment, the same thing is needed from you then. Okay. Khalid, I still have not calculated values. We are not going to do that because this is just arithmetics. We are not going to do arithmetics. Khalid, you want to explain once again how you can get the numbers? Is that right? Okay, so have a look here on our result. Our result is that y squared divided by sine square phi multiplied by something is something multiplied by sinus square plus something. And now those somethings are all constants. The only things which vary are y and phi. Only y varies, only phi varies. The dependence on the parameters is only those places here. I can mark them red with red or something. Okay, here this thing here varies, and this thing here. Things in red are parameters, and everything else are constants. So what you have here now is nonlinear dependence between y and phi. But if you plot that first thing here, the first vector y square over sine square phi as a vertical axis and sine square as a horizontal axis, then you should obtain a straight line, because you have now between those two things, you have linear dependence. You can see that y square over sine square phi is a linear function of sine square phi, which means that if you plot these data, you should obtain data lying on a straight line. You have data points here, somewhere here, maybe not exactly straight, but something close to straight line. And then you draw a straight line through these points, and you can determine the intersection point, so-called abscissa, and the angle over here is a slope angle. So basically, if you have a linear function, as we say here, y square sinus over sine square phi is a linear function of sine square phi, then the factors, this intersection point with the vertical line, and this is a slope tangent. So those two things can be calculated from the graph as the intersection point here, A, and tangent alpha is A. So if you plot the data, you should obtain you should be able to find numerical values for A and B. And once you have numerical values of A and B, then you can relate those numerical values to the constants which you have in the dependence above. So one constant is here, the other constant is here. You combine them, we find that A should be the ratio of those two, which is this thing here. Now we have related thing which we can calculate it from the plot A to the constants. And then we can express something which I needed in terms of that A and the other constants. In this case, m square over q square, we can express from here, using that intersection point A. Khalid, is it okay now? Lama, the reason why you use relativistic mass is that the speeds are relativistic. If you have solved the third part where you ask what is the maximal kinetic energy, you'll see that it is something like 0.6c. So the speeds are approaching relativistic speeds. That's why you need to do it here. Justice comes down to the numerical values, because you have beta. Okay, what is difference actually between normal electron and beta particle? Beta particle is electron, but beta particles comes from radioactive decay, and because of that, it comes with a huge energy. So usually beta particles are relativistic. As soon as you are told that beta particle, you should assume that this is relativistic electron. So why you need to use relativistic mass is because of that. Okay. Lama, are you okay? Now, next topic. As promised, we need to go on and move to the next topic, and we are, as usual, we are running out of time because everything, all solving takes some time. But we would like to discuss a few things more. So, first thing is motion of particles in crossed electric and magnetic fields. Now, let us have a look on the expression what we have for the charge force acting on a particle. So we have F equals E plus V cross B and multiplied by charge Q. Now, but let us say that we go to another frame. We go to another frame in which the speed v, which moves with speed u. And in that case, in that frame, the speed v prime is, or let us say that this speed here is in moving frame, But frame speed is frame velocity is u. Okay, then v prime in lab frame v prime equals v plus u. So that in lab frame f equals e plus u cross b plus v prime cross b, and all multiplied by q. Now this guy here is the velocity. V prime is the velocity in lab frame. Now, did I do it correctly? Well, it's the other way around actually. Yeah, let me write it such a way. I made a confusion with these primes. Let us do it so that here f is v prime is speed in lab frame. So this Lorentz force in lab frame. Now v is in moving frame and v prime is in lab frame. And so this force in lab frame, but this is in moving frame. Now let me just a moment. I'm confusing which one I take over which. So v is lab frame speed. V is speed in lab frame, and v prime is in moving frame. Okay, now I think now it's okay. Now everything is okay. Let us repeat once again. So Lorentz force is in moving frame v prime cross b, and sorry about that. I started talking before thinking properly. So force in v is speed in lab frame. V prime is speed in moving frame. A force in lab frame involves speed in lab frame. Now we plug this expression for speed in lab frame in terms of speed in moving frame. Plug in, and then we obtain an expression for the force in moving frame. And now we have here v prime b, which is clearly the Lorentz force in moving frame. Okay. Now, what is this? Who can tell you? What is this?
Shouldn't this be in lab frame?
Sorry?
Shouldn't this be in lab frame?
U is the speed of the lab frame, yeah.
Yes, so
U is the speed of, okay, what goes into Lorentz force in moving frame, because this is force in moving frame. This should involve speed in velocity in moving frame, and that's here. Velocity in moving frame. You know that Lorentz force is velocity in a frame cross b. And here it is. This is velocity in the frame cross b. This is clearly Lorentz force. But what is that term here? So in lab frame, we have nicely. Force is electric field in lab frame plus v cross velocity in the lab frame cross magnetic field in lab frame. Now we make go to another frame which moves with velocity v. so that velocity in lab frame becomes v prime velocity in moving frame plus u, the speed of the frame. We plug into the formula and we obtain this force expression becomes what I wrote on the second line. And now a force, we know that force must be the same in each frame. So it doesn't matter if force is lab frame force or moving frame force, because that as long as our frame moves with constant velocity, forces are the same. Inertial forces appear only if our frame moves with acceleration, but our frame moves with constant velocity. And so so now we have here an expression which involves a velocity for the force in moving frames, the last formula here, which involves velocity in moving frame v prime cross b, which is Lorentz force. But then apart from the electric field, which we had before, we have additional terms u cross b. So what is that? Khalid, did you understand? Are you okay now with my question? Do you understand what I mean? All right. Then the question stands, what is that u cross b? Now Lorentz force is here. Lorentz force I mark with a green circle here. This is Lorentz force. This is velocity in frame cross b. This guy here is Lorentz force in the moving frame. So this is expression for the force acting on a particle. We know that on particle we have electric field, magnetic field, but there are no other forces. Can anyone guess what is that? What we have? What the additional term which appeared? No, not Coriolis. Coriolis appears if we have a rotating frame, but we don't have any rotation here. What can it be? No inertial force, because our frame moves with constant velocity. Inertial force is only when our frame moves with acceleration. So any guess? All right. Should I tell you, or you would like to think? No, not fictitious. No, this is not fictitious force. Zara, do you have any idea what it might be? No, Khalid, not centrifugal. Centrifugal is only if our frame rotates. This doesn't rotate. No centrifugal. This is, guys, look, this is force which acts on charged particle. Which forces are acting on a charged particle? This is force which is proportional to charge. Which forces are proportional to charge? There are only two forces. Who can tell me what are the two forces? Khalid, no, not right, Khalid. Yeah, electric and Lorentz, completely correct. But Lorentz force is here. It cannot be Lorentz force because Lorentz force is perpendicular to velocity. And but this term here is not perpendicular to velocity. It is perpendicular to the velocity of the frame, but not the velocity of the particle. Lorentz force is proportional to the velocity of particle. So that force is not Lorentz force. So which force it can only be? It can be only electric force. So which means that actually this whole thing here now is a new electric field. So electric field, if we go to another frame, will change. E prime is equal to E plus U cross B. So we have, if we go to another frame, B goes into E. So we concluded that if we go to a moving frame, then actually it appears magnetic flow field goes into electric and the other way around. So now actually I can write you down a generic expression for how to change electric field and magnetic field. So a complete relativistic expression is that E prime, but only perpendicular to the velocity component. So E perpendicular is perpendicular to the speed u, and B perpendicular is perpendicular to u. Let us use these notions. Then E perpendicular nu is E perpendicular old plus u cross B and divided by the relativistic factor 1 minus v square divided by c square. But in most cases, we can take this just 1. And similarly, B perpendicular prime equals B perpendicular plus u, okay, here it goes also perpendicular, u cross E perpendicular divided by c square and divided by 1 minus v square over c square. Okay, these are relativistic formulas to transform electric field into magnetic field. And for if V is much smaller than C, then we can approximately write that E perpendicular is E perpendicular, new one is old plus U cross B perpendicular, and B perpendicular new is B perpendicular old plus U cross E perpendicular old divided by C squared. Okay, approximate formulas. This is how you transform one into another. Is this clear to everyone?
Is it v squared over c squared or u squared over c squared? It's not clear.
Oh yeah, sure, it is U. Yeah, thanks. It is actually U. It is U, sure. All right. Now, what U is this? U is the velocity of the frame. If we go to a frame of which moves with U, then this is these are the new expressions. Now, what is U's for us? The use is that now, if we want to figure out how charged particle moves, if we have crossed electric field, let us say you have electric field down, and we have magnetic field from us, and then we ask how will charged particle move if it has at rest at the beginning. If charged particle have charge E and mass M, how it will move. Now your task is please try to sketch, please try to draw, how do you think this will look like? Please try to draw the trajectory of a charged particle which starts at rest and starts moving due to electric field. How it moves. It draws a trajectory. Sketch trajectory. Okay, this is your task, and please send me as soon as you have got something, please send me. And the hint is that please use the previous results what we obtained. Now Llama wants to go back. Okay, here you are. All right. So actually, the hint. What is the hint? The hint here, additional hint, is that I suggest you to use frame where one of the fields disappears. One of those fields disappears. And let us say that electric field is relatively weak, so that the field which can disappear is electric field. So I use frame where E prime new electric field is there. This is a question. This is a hint how you'll be able to. No, it is not sinusoidal, Khalid. It is not sinusoidal. Please, yeah, please make a sketch. All right. How are you guys? Have you any result? Okay, let me help you a little bit. What is a trajectory in, if we find a frame where there is no electric field, what is trajectory in that? Lama, what do you think? Okay, yes, Khalid, yes, circle, sure, it is circle. This is circle for sure. And now you just need to figure out what is a shape. If in one frame you something draws circle, but the frame moves. So we have in one frame, it moves along circle. But now our frame itself is moving. So what is a shape in the frame if it moves along circle in one frame, but frame is moving? What kind of shape? Can you please try to sketch what the trajectory could look like? And you can send me by email, or you can, yeah, whatever. You can try drawing here annotation on the screen, whichever you like. No, well, velocity, what we had before, it moved along helix, but now it is not helix because in the previous case, we had motion along Z, but circle was in XY plane. But now we have rotation in XY plane and motion in along X. So it is not exactly like before. Because if E is from upside down and B is from us, as shown here in the figure, then if we go back to here, we had now that additional term is U cross B perpendicular. So additional for which appears for electric field. So E prime nu is E plus U speed of frame cross B, and this must be 0. So U cross B is E. And now we want to know what is U. So now suppose that B and U are perpendicular, and then we take now cross product. Guys, do you know how to make a double cross product? We have U cross B cross, let us take cross product with B. What happens? U cross B cross B. Can you do you know how to simply you can open the braces here? Have you worked with something like that? Have you made a double cross product? Anyone? Zara, do you know double cross product? How to simplify this thing here? Okay, we have formula A cross B cross C. Oh, sorry, cross C, like that. And then this thing here equals to Butts minus sub. So it's a famous Butts minus sub formula. Okay. So double cross product can be expressed in terms of dot product. And now if we take this thing here, this would be B dot U dot B minus U B square. B dot B is B square. Now, because U is perpendicular to B in our, according to our assumption, so this goes away. And so we have U cross B is UB square. And so all things together, after we take a dot product from this expression here, if we take cross product, then we obtain minus U B square equals E cross B. So we can say that U is E cross B divided by B square. So the direction is perpendicular to both E and B, and minus. So actually, what is B cross E actually, which equals B cross E divided by B square. The speed of the frame where E disappears is B cross E divided by B square. So modulus, U modulus is E divided by B, and direction is perpendicular to both of them. All right? So, why do we need the double cross product? Well, double cross product was I used this in order to figure out the direction. As you can see, it simplifies to simple ratio. But if you want better sign, then it's good to write in dot product as a cross product. I obtained this expression here, which I framed here. I can frame it, which I framed with red color here right now. I obtained this by taking cross product of this equation here. I took cross product with B. I took cross product of left hand side and right hand side, and then I obtained this expression here. And this is a nice convenient expression which gives both direction and modulus of the velocity of the frame where electric field disappears. Lama, is it okay? Lama, is it okay? So a cross product was I took double cross product just to have direction, not only modulus but direction. If I cared only about the modulus, then it would have been enough to take just divide. But here I wanted to have direction as well, because the question here important question is what is the direction of our frame? And now we see that we need to take B cross C. So B is from us and E is down. B is from us and E is down. So we turn from B to E, and our frame goes to here. Okay. This is our view of our frame, which is by modulus is E divided by B. Yes, Khalid, exactly. It is like rolling circle. Exactly, it is cycloid. The shape is a cycloid because rolling disk does exactly that. That in co-moving frame, a point marked on a disk moves along circle, and in lab frame it is a cycloid. All right. Now, did everyone understand that it is cycloid? Now, depending on which means that depending on initial velocities, you can have trajectory like that, like cycloidal trajectory looks like that. So this happens in this case, in particular, particle starts from rest. Okay, in the previous figure, when start a particle, okay, let us take new frame. So we had situations that electric field was moving down, was pulling down. So now what happens with the particle? It starts moving down from rest, and then magnetic field starts curving it, but velocity grows, curvature radius becomes bigger, curve becomes flatter, and then it goes symmetrically up and reaches again point where it stands, and then it again goes like that and repeats itself. So exactly when initial velocity is 0, and then it moves along cycloid like that. But if initial velocity is not 0, then you can have different options. It can go like possibilities for cycloid like that, or you can also have like something like that, wavy pattern. It all depends on the initial velocity. If initial velocity is bigger or smaller than E divided by B. So here, initial velocity is opposite, and smaller than V is smaller than E divided by B. But here we can have, like we know, the initial velocity is either opposite along the frame U, or V is bigger than E times E divided by B. Then you have something like wavy. Everything depends on initial velocity now. Is this clear? What do you mean for the one down, Khalid? Yeah, so I speak about modulus of the velocity. So which one? Whether we have A, B, or C. A happens if particle starts from the rest. B happens when you have like a particle starts moving from up, and then let us see. If it's if drift is that way, but particle starts, let us say, from here, from going up, and then in that case it goes like that, but on the other hand, it cannot be. Well, you can figure out yourself exactly what conditions must be satisfied, but whether it is A, B, or C, this depends on initial velocity. Shape depends on initial velocity. That is important. You can always figure out by yourself the speed of the frame and the radius of a circle. You can work out like that. Okay.
Can you explain figure A?
Which part?
A.
A. Okay. A is a particle starts from rest and starts moving in the direction of electric field, down. And then as it accumulates speed, more stronger magnetic field will start acting. Now the curvature radius is related to the velocity. We know that here magnetic field well, actually, now we have also electric field. It's not that easy, that simple to figure out. Still, the easiest thing is to think about go to a moving frame where it moves along circle. So this shape, the important thing is that it starts from rest. Now, if we take cycloid, so cycloid, what is cycloid? Cycloid is you have disk and you mark a point on the disk and consider how it moves. If you point on the rim, then when the disk is in contact with Earth, then the point is at rest. And then it starts rolling, it rolls that way, and this point will start going up and moving like that. The marked point draws a cycloid. Now, on the other hand, if you mark the point here on the disk somewhere here, then at the first this rolls, and this point here moves now, right now moves in the same direction. So and now if it's rolled so that it is the marked point is now here, then it is still moving in that direction. We see that the marked point always moves in the same direction, does not reverse, does not stop. So it moves something now like that. Okay, the mark point moves now like that. On the other hand, if you mark a point which is below disk, let us say that we have disk rolling that way. So we like something like yo-yo, that it rolls on this circle here, but we mark point somewhere here. So if it rolls that, at this point moves to left, and then once it has reached this point here, it is up here, and then it moves to right. So now the circle shape looks something like that. Okay. All right. So it depends on where you mark the point on the disk. In terms of magnetic field, it depends on where you mark the point on the disk. In terms of charge in magnetic field, it depends on initial velocity. In terms of disk, the shape depends which point you mark on the disk. In terms of charge in electromagnetic field, it depends on the how relates what is the value of V initial as compared to electric field divided by magnetic field. The ratio of these two determines the shape. Okay. Lama, electric field does accelerate the particle. Sure, I'll explain this once again. And now let me see a question of Khalid first. Why electric field vanishes in this frame? Electric field can... Khalid, so it is exactly what we did frames before. I tried to show you how and why we have magnetic field going into electric field and the other way around. So I started from writing down expression for the expression for the Lorentz force and Coulomb force. So I started writing this expression here. And then I went to a frame which moves with certain velocity. And then I obtained force in new frame. And then we learned that actually we have something here which can be only new electric field. So we saw that if we have a magnetic field and go to a moving frame, then there appears electric field, or electric field becomes different than it was before. So electric field, magnetic field will, in moving frame, will give rise to certain electric field. And now we can select the velocity of the frame so that the appearing electric field cancels out exactly the old electric field, so that the new electric field is 0. That is so the whole thing is summarized in this two. Now, what happened? What happened? Okay, yeah. It can be summarized by these Lorentz transform formulas. This here is Lorentz transform formula. Lorentz transform for E and B. So in electrodynamics, electric field goes into magnetic field and the other way around if you change frames. Yeah, we have, yeah, U cross B is minus E, yes, exactly. We choose U so that U cross B is minus E, exactly, Khalid. That is the point. Now, as for Lama's question, let me try to show you how. Okay, the most convenient way is to consider this in a frame where there is no electric field. But of course, you can try to consider this also in the lab frame. If you let us consider the same things that we have electric field and magnetic field. Electric field is down, magnetic field is from us, and now we have particle here. And that particle starts moving, and it moves along electric field because it is at rest and no Lorentz force acts because it is at rest. So electric field starts accelerating it down, and now it moves down, but now it has caused a certain velocity. And now magnetic force starts acting, and that starts curving, and then it curves and curves and curves. And the more it goes down, the stronger more the magnetic field curves. And then at certain point, it starts going up. But now the picture must be symmetric because velocity at equal positions here are equal due to energy conservation law. And the directions are symmetric, so you can see that actually this must be mirror symmetric. So it goes up exactly in the same way. And then it stays at rest and process starts repeating. So you can, in such a way, if you think about forces, you can see that this shape is exactly something what you will obtain here. Lama, is it okay now? Lama, is it okay? Did I answer your question?
But won't the velocity change and increase?
Sorry, once again?
Won't the velocity increase because it's accelerating?
Yes, velocity increasing. The velocity is maximal here. V is 0 here. V equals V maximal here. Yes. But here it has already turned here. And if it continues going, magnetic field will start turning it up. And velocity has reached maximum, and then magnetic field turns up. And now magnetic field starts decelerating it. Now velocity becomes smaller.
Yes, yes, I
Because
understand.
now it goes up. Yeah. Does it make sense?
Yes, yes. Thank you.
Okay, and now actually the time is over, but I'm going to give you a small homework. And the small homework is as follows. Now, similarly to before, with that focusing thing, we have now here a source of electrons. Electrons go with all directions with different velocities. But now we have magnetic field B, and we have electric field E. And we want to put here a screen so that these electrons, which starts going in all the direction, will gather all to a single point on the screen. So what should be the distance to the screen so that we would have focusing on the screen? L so that electrons focus on the screen. What should be L? Okay, is the task clear? We have B.
Is that phi or A?
Sorry?
Is it A beside the V? Or what is it?
This is your homework. You don't need to tell me immediately. Once you have done, please solve it properly and send me by email. So what is given is B is given, E is given. And now there is a fixed, at fixed positions, there is a source of electrons. Source of electrons. But electrons goes in all directions with certain small velocity. And now we ask where you should put screen so that all the electrons would gather on the screen. All right, is the task clear? Not the same speed. There is like in the previous problem with the focusing, different speeds. Okay. Different initial speeds, but they start all from point P. Fixed point P, where they start. Is it clear? Different angles they are. The angles different. Different speeds, angles. Different speeds, different angles. Zara, is it clear? Lama, is it clear? Okay. Khalid, is it clear? Mohammed, is it clear? Okay, then I think we can finish for today. And then good luck with your homework and see you tomorrow. Yes, I'll upload the recording today. Did I give you the link for the previous recording? Okay, the link actually, guys, the link is the same as during the previous training. I just added to the playlist the new recording. So it is over there. And let me see, I can probably give you here right now also immediately. Just a moment. See if I can find it fast. Yeah, probably that one. Good work getting it fast. So I'll upload the new video also there. It will be uploading during night. My internet is not very fast, so it will be there definitely by tomorrow morning. All right, then see you tomorrow. You are all very welcome, and see you tomorrow. Thank you for working hard with me, and see you tomorrow. So yeah, the last, as you can see in the link, what Hussein sent, the first lecture is already there. The yesterday's lecture is already there. Okay, bye-bye. See you tomorrow.